Hey guys, this video is on solutions and how they form. So let's talk about what a solution is first. A solution consists of a solvent and one or more solutes. The solvent, if it's a homogeneous mixture, then it's just whatever there's the most of. For example, the air that you're breathing right now is a homogeneous mixture, and nitrogen gas would be the solvent because that's what there's the most of. If it's a heterogeneous mixture, let's say we take some salt and dissolve it in water or something like that, then the species that dissolves the others is the solvent. And we're going to talk about exactly what that means in a few minutes to dissolve something. The solute or solutes are everything else that's in a solution that's not a solvent, not the solvent. There's one solvent. So solubility is defined as the maximum amount of a given solute that will dissolve in a given amount of a given solvent at a particular temperature. Now there's a lot of parts to that definition and they're all important. It depends what the solute is, depends how much solvent we have, what that solvent is, and what the temperature it is. Because as you change the temperature, solubility changes. But once we've reached this point, the solubility, that solution is said to be saturated. When we've dissolved the maximum amount of a given solute in a given amount of a given solvent at a certain temperature, that solution is said to be saturated. Now, before that point, when we haven't dissolved that much solute, that solution is said to be unsaturated. Now, we can also have a solution that is supersaturated. And the best way to talk about this, I think, is to describe how we might do that. It ends up that sodium acetate will form a supersaturated solution when it's dissolved in water if we follow this process. So what we do is we take some water and dissolve some sodium acetate in there and keep dissolving it until we've saturated that solution. And then we start heating up the solution. Now it ends up that with sodium acetate in water, as you heat the solution up, the solubility of sodium acetate increases. And that's not the case for everything, but it is here. So we heat it up, maybe dissolve some more sodium acetate in there, and get it to this high temperature where we have a lot of sodium acetate dissolved in there. Now, if we cool that solution down really carefully, don't disturb it, don't bump it, and if we start with a clean beaker and nothing is contaminating it, then as we cool this down, we can get down to a lower temperature where the solubility is less and still have all of that sodium acetate dissolved in there. That's a supersaturated solution. We've exceeded the solubility, but that's an unstable situation. So if we disturb that system in any way at all, sometimes even if you flick the beaker with your finger, it'll disturb it enough. Or you drop a seed crystal of sodium acetate in there, then the excess sodium acetate, or whatever the solute is, will start crystallizing out. And it looks like these last two pictures, which it looks really cool. Okay. That's supersaturated. So these are some examples. This is an example of a solubility. And all the parts are here. So you might be given the solubility, say, of sodium chloride, that's a solute, in water, that's a solvent, at 20 Celsius, that's a temperature, and it's 359 grams per liter. So the volume of solution is 1 liter, and that's taken to be an exact 1 liter. Now, if we change just one part of this, the solvent, instead of water making it methanol, the solubility changes quite drastically in this case, from 359 grams per liter to 14.9 grams per liter. Now, for a saturated solution, solubility is a conversion factor. So we're talking dimensional analysis again, guys. It ends up, so what we can say, for sodium chloride in water at 20 Celsius, 359 grams of sodium chloride will dissolve in is equal to exactly 1 liter of solution. So let's do an example. We're given the solubility of cobalt-2 fluoride in water at 20 Celsius, 1.36 grams per 100 mils, not per liter. We want to know how much cobalt-2 fluoride will precipitate out if we do this. So what we're going to do is we're going to take 250 mils of water, add 3.25 grams of cobalt-2 fluoride to it. First thing we're going to have to do is see if all that will actually dissolve. And then, okay, once we do that, then we're going to evaporate. So we're going to boil that solution, and we're going to evaporate 129 mils of water. And then we're going to, I didn't say it here, but we're going to cool that solution back down to 20 Celsius again. And so now because we have less solvent, we'll be able to dissolve less of the solute, the cobalt-2 fluoride. What we want to know is how much of that cobalt-2 fluoride will precipitate out, will fall out of solution. So why don't you guys go ahead and work this out and come on back when you get an answer. Welcome back. So first let's check and make sure all the initial cobalt-2 fluoride will dissolve. And so all we're doing here, guys, is dimensional analysis. So we want to know how many grams of cobalt-2 fluoride, is equal to 250 mils of solution. And the conversion factor is the solubility, 1.36 grams per 100 mils. And it ends up, we can dissolve 3.40 grams of cobalt-2 fluoride in 250 mils of water at 20 Celsius. We only put 3.25 grams in, so yes, it should all dissolve. So now that we know it all dissolved initially, now we're going to figure out how much solution we have left. So we evaporated out 129 mils, subtract that from the initial 250, and we see that we have 121 milliliters left. So now we do the same sort of calculation down here, only we see now how much cobalt-2 fluoride will stay dissolved in that smaller amount of solvent, the 129 mils. So same idea, it ends up that about 1.65 grams of cobalt-2 fluoride will, that's the saturated solution, that's how much will stay in solution. Everything else will precipitate out. So we put 3.25 grams in initially. At this point, after the evaporation, only 1.645 grams will stay in solution, so we'll get 1.60 grams precipitating out. PPT here stands for precipitate. So there we go. So now let's talk about what affects solubility. So what we're going to do here is first talk about the process of dissolving a solute in a solvent. And we're going to use as our example an ionic compound, say sodium chloride dissolving in water. So in my picture on the left here, the blue circles would be water, the yellow circles would be sodium ions, and the white circles would be chloride ions. And the solubility of any solute in a solvent depends upon the relative strengths of the intermolecular forces, the intermolecular forces between the solute particles with themselves, between the solute and the solvent, and the solvent particles with themselves. But overall what happens is, as we put that crystal of sodium chloride into the water molecules, we know water is a polar molecule, so it has a positive end and a negative end. These are going to interact with the positive and negative charges on these ions here and start pulling them away from the other ions. And when they do, when they get them pulled a little bit away, they start creeping in and surrounding them, and it ends up that we get these ions all surrounded by solvent particles, in this case by water molecules. And here, this picture over here is what it looks like when these ions have been dissolved, solvated, surrounded by water molecules. In this case, we would say that they're hydrated because the solvent's water. And there's actually, this is a two-dimensional picture, but in reality it's a three-dimensional picture. And so it's like basically a sphere of solvent particles around the solute particle. We call that sphere the sphere of solvation, or in this case the sphere of hydration, because it's water. Now, the intermolecular forces that we're talking about here, should be partially a review from Chem 101. We know that there are dispersion forces, also called induced dipole, or maybe van der Waals forces. We have dipole-dipole forces. We have hydrogen bonding. And while this isn't really an intermolecular force, we're going to clump it in here for our purposes, the interactions between the ions, the ion-ion forces. And in a solution, some of the combinations that we see are the interactions between an ion and an induced dipole. This might be an example of putting an ionic compound in a nonpolar solvent, like say hexane or something. Or dipole-induced dipole, so it might have a polar solute in a nonpolar solvent, or vice versa. Or maybe an ion-dipole interaction, an ionic compound dissolved in a polar solvent. The relative strengths of these interactions are what are going to determine, or be one factor in determining whether or not something will actually dissolve. So the types of solutions that we can have, basically any combination here. So if a gas is a solvent, We could have a gas as a solute. We could have a liquid as a solute. We could have solid as a solute. If a liquid is a solvent, we could have a gas as a solute. Can of beer. We could have a liquid as a solute. We could have a solid as a solute, and and then we can keep on going, right? So you get the idea. These are the ways we can form different solutions. Now what we're going to talk about, guys, are the energetics of solution, of making a solution. And what we're going to do is we're going to make use of the wonderful property of enthalpy, that it's a state function. Remember, a state function is a function whose value only depends upon the state that it's currently in and not how it got there. Which means that because we're talking about changes in enthalpy, that's what the delta means. The change in enthalpy for a process, because it's a state function, only depends upon where you start and where you end up, and not the process that you take to get there. And so what we're going to do here is we're going to make up an imaginary process. It's really nice because it ends up, we can find the change in enthalpy for all the steps, which will allow us to calculate the change in enthalpy for the overall process, which will be the same for the real process. So the first step here, step 1, is to dissociate the solvent particles from each other. We'll call this change in enthalpy delta H1 for now. So let's say our solvent is water. So what we're doing here is we're just pulling the water molecules apart from each other. We're not breaking them apart, but just pulling them away from each other. And so what we essentially have here is a gas. This delta H is always positive. We always have to put energy in to pull particles away from each other. That's always an endothermic process, positive. Step 2, we're going to take the solute and dissociate it into gaseous species. Now, for our example, we're going to use an ionic compound, let's say sodium chloride. So we're going to take solid sodium chloride and dissociate it into the gaseous sodium ions and chloride ions, sodium ions and chloride ions. This is the exact opposite of the definition of lattice enthalpy. If you remember back in Chem 101 when we talked about the Born-Haber cycle, we defined the lattice enthalpy of an ionic compound as the change in enthalpy for the process of taking the gaseous ions and combining them to form the solid ionic compound. So what that means for us, guys, is if we can look up the lattice enthalpy for an ionic compound, the delta H2 for this process here is just going to be the negative of the lattice enthalpy. We define lattice enthalpy as being the change in enthalpy for taking the gaseous ions and forming the solid compound. That's always going to be a negative number, so this will always be a positive number. Now, if this is not an ionic compound, then it's the same idea though. Let's say this is ethanol, is the solute. Then all we're doing is we're separating the ethanol molecules from each other. Now we're not breaking the molecules apart, we're just pulling them apart. So this process would be the heat of vaporization, going from a liquid to a gas. But here we're doing the ionic compound, lattice enthalpy. And step 3, at this point now, guys, we have the solute particles all separated from each other. We have the solvent particles all separated from each other. And now we recombine them and we get the solution where the solvent particles have surrounded each of the solute particles. Now the change in enthalpy for this process, which we'll call delta H3, can be either endothermic or exothermic, negative or positive. And it depends. And it ends up that the first step, the delta H1, plus this step, delta H3, change in enthalpy for this is called the enthalpy of solvation, or delta H of solvation. Heat of solvation is another way of saying that. And if the solvent is water, then we can also call this the heat of hydration, or the delta H of hydration. So because enthalpy is a state function, if we add up the delta H for all these individual steps, that gives us the delta H for the overall process, which we call the heat of solution. All right, so now guys, be careful. We have to be really careful about words here. This is the heat of solution, different than the heat of solvation. Okay, that's one of the steps, or two of the steps. So delta H1 and delta H2 are always positive or endothermic, and delta H3 can either be exothermic or endothermic, which means that for the overall process, if delta H3 is greater than the sum of delta H1 and delta H2 and it's negative, then the overall process, the heat of solution, will be negative exothermic. But if delta H3 is less, the magnitude of delta H3 is less than the sum of delta H1 and delta H2, doesn't matter what its sign is, it's always going to be overcome by this, and the overall process will be endothermic, positive. So now let's do an example. So we're given the lattice enthalpy of cesium chloride as negative 657 kilojoules per mole, and we're told that the heat of solution, this is the overall process we're talking about here, is positive 17.2 kilojoules per mole. We want to calculate the heat of hydration, or solvation of cesium chloride. So why don't you guys go ahead and work this out, and when you get an answer, come on back. Welcome back. So delta H of solution, the heat of solution, is the sum of the delta H's. But we know that delta H, what we call delta H2, is just negative of the lattice enthalpy, which we're given. And delta H1 plus delta H2 is equal to the heat of solvation, or in this case, heat of hydration, because it's water, the solvent is. So that means, substituting in here, the heat of solution is equal to negative lattice enthalpy plus the heat of hydration. Or, remember what we're asked to solve for here was the heat of hydration. So you have to be really careful about the words, right? And we're given the other two. So if we rearrange this, we see that the heat of hydration is equal to the lattice enthalpy plus the heat of solution. So we know that both of those numbers, all we have to do is plug them in. Negative 657 kilojoules per mole for the lattice enthalpy, positive 17.2 kilojoules per mole for the heat of solution, and we get our answer. The heat of hydration is about negative 640 kilojoules per mole. So in this case, it's an exothermic process for the hydration, even though the heat of solution is positive, which we'll talk about right now. So just like we saw for the cesium fluoride, for potassium chlorate, its heat of solution, remember that's the overall process, is positive. It's an endothermic process, positive 41.38 kilojoules per mole it ends up being. But if we have to put energy in to do this, how can and it is spontaneous. We know if we take some solid potassium chlorate, put it into water, it spontaneously, by itself, dissolves. How can that be? It ends up, there's another really powerful driving force called entropy. Now what we're going to do here is just introduce you guys to the concept. We're going to come back in a later module and delve into this a little bit more. It's a symbol for this property, entropy, is just capital S. The definition, its entropy is equal to some constant K called Boltzmann's constant times the natural log, this is ln, natural log of omega or W, which is W stands for the number of energetically equivalent states the system can be in. So what entropy is, it's a measure of how spread out the energy of a system is, how many different ways there are of equivalently distributing the energy in a system. Now you'll see if you Google this, people talking about entropy as being a measure of disorder. That's really misleading. It's really a measure of how many energetically equivalent states the system can be in. We'll get into that in a later module. K is the Boltzmann's constant. So remember our process here, our spontaneous endothermic process, dissolving potassium chlorate. Well, for this process, because it ends up being, we know from observation that it's spontaneous, that means that the entropy contribution, again, we're not doing any calculations yet, we'll get to that later, overcomes the endothermic part of this process, and it happens spontaneously. We have these two things. We have the change in enthalpy and we have the entropy, right? And it ends up that just because the entropy is large enough in the solvated system compared to the unsolvated system, this happens. That's what makes this happen. That is the driving force. Now, sometimes that's not enough. Let's say if we try to dissolve some oil in water, we know that won't happen, because even though if the oil were to dissolve in water, we would increase the entropy, and we have more. It would be the energy would be more spread out. It ends up that the endothermic part of this process overwhelms that, and it does not happen spontaneously. Again, just an introduction. We'll get into that more. And that's all there is to